Good evening, welcome to my laboratory. Here we go again. Okay, I realized after somebody sent me a PM that I had one of those flashlights that have a great big array of white LEDs in it. So I sacrificed the flashlight to the over Unity gods and took out the board. There's 24 LEDs there. They were originally all in a strict parallel arrangement with a 3 AA battery power supply. But I rewired the circuit board a little bit so that now there are two 12 LED parallel arrays, and then those two 12 LED parallel arrays are in series to make a series parallel stack, and then those are actuated by this here, and it takes about 5 volts on a DC source to get these things glowing brightly. Okay, I hope you'll take my word for that. And then I stuck him, made a little pin there and stuck him in there. So that's the load, 2N2222 transistor, and I'm monitoring the output voltage, the collector with respect to that point there, with 2 oscilloscopes, and that'll be the top trace of this oscilloscope, and there's its 0 baseline, and that'll be the center over there on that oscilloscope. And then down here we'll be looking at the current across the 1 ohm current viewing resistor down there. Okay, and so I don't even have a battery on there now. What I've done is I've just I wanted to see what would happen if I put a solid 1.5 volt charge on that capacitor by using my nice Topward regulated power supply down there. And so that's what I did. I carefully adjusted it so that the resultant voltage on the capacitor is just about 5 volts. Okay, so and it's holding that right now, and it's actually being powered, but I'm going to turn that off in a moment, and then we'll turn the Joule thief array on. And I'm also using, instead of using the toroid like I was before, I'm using my favorite inductor, which is this little bitty one here. It's about 21 millihenries each coil. Powerful lot of inductance in that little sucker. And it works great in the Joule thief. Okay, and I've also got some ideas about the scope traces that may help to improve performance still. All right, so now let's go ahead and I will turn off the charging to the capacitor, and it's not even going to drop. It's solid. All right. Okay, so now we'll disconnect the power supply altogether. Okay, and looks like that capacitor is holding pretty well. Alright. Haven't turned the Joule thief on yet. Okay, so everything's ready. So now we'll go ahead and turn the Joule thief on. I think. Yeah, there it is. Whoa, Nelly. I think you can see that those lights are pretty darn bright. And the voltage starts dropping, as it should. And then over here on the oscilloscope, you got a trigger here. Okay, so the top trace is the voltage on the collector. Sorry about the light. Let me get some illumination there. Okay, so the top trace is the voltage on the collector, and that's being read at 5 volts per 5 volts per division. So we're seeing that actually the LEDs, I finally figured out that the LEDs are on, I think, when we have the voltage goes low, and then this top part is when the LEDs are off. I could be wrong about that. Still, it's damn confusing. Okay, and then this is the current profile here, and that's being viewed at 20 millivolts per division, and so that's a 20 milliamp per division spike. So that's 1, 2, 3, 4. That's about 80 milliamps in that spike, but there's not a lot of energy there because it's so narrow. Okay, so, and then there's another view of the voltage trace over there. Okay, so we're still nice and bright. I forgot to note the time when we started. what I think is a good idea is probably to time how long it takes to make exactly 1 volt drop. So to go from 1.5 volts down to 0.5 volts, in other words, because the LEDs will still be, the LEDs, man, once you get down to below 1 volt, like into the 0.7 and 0.6 volt range, the LEDs are clearly glowing at that voltage, and they just keep on glowing. And I've actually had this thing going for over 10 minutes with good perceptible light in there, and that's only a 3 farad cap charged to 1.5 volts. Okay, so right now it's not hooked up to any power supply. It's just running on the capacitors. And we still haven't dropped a full volt yet, but you can see that the current has really gone down, and the frequency changes. First it goes up and then it goes down, so there's kind of a wandering of the frequency. Right now it looks like the frequency is lowering, it's decreasing. Right? Get that trace moved off kind of to the side, don't I? That's better. Okay. And the LEDs are dimming, but I think you can see that they're still plenty bright, and still losing voltage. Okay, now what I think about this is that you want a low frequency and you want a broad spike. I think that will give you the least current drain, the least power. I could be wrong about that, though. I still have to do some more research to confirm exactly what's going on with that spike as regards to the voltage. All right, so now we're down into the below 0.6 of a volt range, and so if I were actually timing my 1 volt drop, I'd be getting ready to stop the clock. But the LEDs, as you can see, they're still pretty bright. I mean, you could read by that light if you didn't have this light on. They're starting to get a little blue tinge to them, so we know we are running down. And I think you can tell that the rate of the rundown is decreasing. And so once it gets down to 0.500 volts is about when you would stop doing the timing of your 1 volt drop. And it's about time to switch ranges on the scope there as the voltage decreases. The current's a very interesting trace there. Okay, so now click, you'd stop your clock for the 1 volt drop in the battery, but LEDs are still doing great. Now, of course, this is only 24 LEDs, it's not 38, but it's all I could, I mean, I sacrificed a flashlight, a perfectly good flashlight for this. It's only 3 farads, not 10. Now, another interesting thing that I found, actually, that kind of surprised me is that the circuit keeps oscillating long after the LEDs go out. If you keep tracking it on the oscilloscope, the circuit's still oscillating when you're down to 0.3 of a volt or even below that. And that's using a 2N2222. If I used a different transistor, I think I could get it to oscillate even below that frequency. And this is a 1-to-1 coil here. But I've actually had it powering 7. This array right here is 1, 2, 3, 4, 5, 6, 7, 8, 9 series groups. Nine groups of 4 parallel LEDs, all of them in series. And this circuit will light those. It'll light those 9 series LEDs with each position made up of 4 parallel LEDs. Okay, and you can see now that the rate of the voltage decrease has really slowed. And so, you know, one might be tempted to call this a forever light, even though it's getting kind of dim. It's still glowing. But if you recharged at 1 volt, let's say that you had an automatic recharger, or I'm sorry, at half a volt or 0.75 volts, you only dipped down part of your voltage range before you got dim, you certainly could keep things going for a long time. The question is, though, is it better to do that or just leave the battery hooked up? Because charging the capacitor has some inherent losses in it. And as you can see, we're still oscillating, but now the frequency has started going back up again. Isn't that weird? First it decreases and then it increases. So if I had a 10 farad cap, that would be 3.3 times as much energy that I could use, because the energy on a cap is linearly related to the capacitance. It's related to the square of the voltage, though, proportional to the square of the voltage, so you get more bang for your buck. Even if you go from 1.3 volts to 1.5 volts, that's a significant energy increase in the capacitor, and so you really need to be precise about your voltage measurements. The voltage readings that you take from the meter on the power supply are not good enough for quantitative work. You have to follow them up with the use of an accurate and precise voltmeter, and you don't see them around very much anymore, but at one point Simpson was the name for analog meters, and this is one of their digital meters, and it works pretty well. I have no complaints about it. Alright, I think those are, you know, they're dim now. I'd call those dim. But they are still glowing, and they are still oscillating. Thank you for watching.